As you said, I'm a second year PhD student here with Mark. And this talk is basically going to be a summary of two papers that I wrote together with Mark and Greg Pavliotis, who's at Imperial, on, as you said, neural parameter calibration. And essentially the idea is using neural networks to calibrate physical equations, physical models to a data set, calibrate the parameters of the equations to a data set using neural networks. And I basically structured the talk to just show you kind of the features, the applications, the results of the method. Of course, I'll give you an overview of the method itself. If you do have any technical questions, then please ask and I can go into the details. Yeah, so the basic idea is that we want to use a neural network to obtain parameter estimates for complex system models. So these are differential equations that describe large systems, network systems, these sorts of things. But at the same time, we want to leverage the training process to get probability densities on the estimates. So we don't just want to get an estimate, we want to get some kind of uncertainty quantification on the estimates. And the basic idea is that we assume we observe some kind of data, T, time series data, steady state data, any kind of data, and we input that into a neural network, which then outputs a set of parameters. And these parameters we then insert back into some kind of set of equations. We run a numerical solver, we solve the equations, for example, using an agent-based model or something like this. And the numerical solver will obviously produce a predicted data set. And by comparing the two, we get a loss function, and a loss function we can use to train the neural network. And by training the neural network, I mean iterating this loop multiple times until the neural network converges to a steady state. And we found that this methodology is very powerful and very useful and very flexible. So for example, I mean, what you're basically doing is fitting a model, a physical model, to the data set you have. And you may have a pretty large data model mismatch. It may be the case that the observed data you have isn't described perfectly, isn't described very well at all by the equations that you're using. But nonetheless, you can try and optimally fit the equations to the data you have under the constraints. You're not running any kind of inverse problem, so you have a lot of flexibility. For example, when the system is underdetermined, it may be the case that lots of parameters fit the data you have, that there are multiple sets of parameters that all solve the equations optimally under the constraints. The method can deal with that, no problem. And we found that it's very fast, computationally very efficient, very accurate, and doesn't need a lot of sort of data pre and post processing, so it doesn't need any kind of mathematical magic. And I'll kind of walk you through the examples and yeah, in the next slides. Okay, but this is just solving an optimization problem. I said that we also want the probability density. So how can we get probability densities out of this? Well, we can exploit the fact that the training process is, in a sense, a kind of sampling, right? Because as the neural network trains, it sort of traverses this parameter space. It calculates a loss value at each point it samples, and we can collect all these loss values and get this sort of loss potential. So in this example, we want to estimate two parameters, alpha, beta, say. This black dotted line is just one example trajectory that the neural network might take as it sort of meanders through the parameter space and eventually lands at one of the two minima that this function has. So this is a non-convex function. There were two sets of parameters that both solve the problem equally well. And if we want to increase the sample density, we just train the neural network multiple times. We just repeat this. And we can do that in parallel, of course, because the different sampling runs don't depend on one another. So you can just train the neural network multiple times, increase the sampling density, and this way you can deal, for example, with non-convex problems. And you can sort of see, I'm not going to go into details, but you can sort of see how this will give you a joint probability density on the parameter, right? This sort of loss potential already looks like a probability density, and then if you want the densities on the individual parameters, you can marginalize over the joint probability distribution, etc. Okay, and so now I'm just going to go through 4 examples that we looked at in the papers, and that kind of showcase different situations, different scenarios that hopefully are of interest to you. So the first example is maybe the least engineering related example. It's just a very simple kind of classic toy model of the spread of infection. I don't know if you're familiar with the SIR model. It's a simple agent-based model of the spread of infection. You have a set of agents on a domain, which is periodic in this case. And in this model, there are three types of agents: those who are susceptible to the disease, those who have been infected, and those who've recovered. And you kind of plant an initial seed of infection somewhere on the domain, the infection spreads, and eventually everyone has been infected and everyone has recovered. So it's just a very simple model. And what we're interested in is getting the relevant parameters for the dynamics from this data set. So the relevant parameters are things like the infectiousness, the recovery rate, and maybe some kind of estimate of the noise. And we do that by fitting this system of stochastic differential equations to the model. So this is kind of a smooth model of the discrete dynamics. It describes the rate of change of the densities of the three types of agents, S, I, and R. And you can see there are sort of three scalar parameters. There's beta, which is the infectiousness. There's tau, which is the recovery time. And then there's sigma, which is a kind of noise level, so how noisy is the system. And what we observe are these densities. So these are the densities of the three agent kinds. Light green is susceptible, red is infected. You can kind of see this sort of classic curve of the infected population that we saw during COVID, for example. We sort of get these peaks. So these are the densities that we observe, and from these observations, we want to kind of extract the relevant parameters by running the neural scheme and getting it to fit these equations to the data set. Now, the key point is that these equations don't actually describe the discrete system, because these are smooth in time and space. So these are a sort of mean field limit. And this is kind of, I mean, in the real world, you wouldn't know or care about the position of each individual agent, each person in a city or in a country, right? The only thing you kind of see are these densities. You know how many people have been infected in total, how many people have been recovered, have recovered. But you don't know, where each person is or what, it's impossible to do perfect contact tracing. So but these are kind of smooth limits of the discrete system. So there is a data model mismatch, which is intentional. We're trying to sort of see how it performs when there's a gap between the data and the model. And so what we do is we run the neural network and we get these marginal densities on each of the three parameters, which is showing one here, the infection parameter. And as you can see, you get a really nice density. The red dotted line here is the true value, so it's an infection probability of about 20%. We recover that value with an error, and we not only get the prediction about the value, but we get an uncertainty quantification. And the uncertainty quantification, and I'll show that throughout the talk, is expressive of the noise on the data and the kind of uncertainty in the model itself. So the non-convexity, the loss function, these sorts of things. And as you can see, running the neural scheme over 20 different initializations on a standard laptop takes about 45 seconds. So one of the main advantages of using neural networks is they are very fast. And I'll come back to that as well. And then what we can do is we can take the sort of predicted value, we can plug it back into the equation and see how good is the calibration, so how good is the fit, what is the kind of best fit we get. So this plot here are the fitted densities. This is the data set, these are the fits. And you can see that it's a decent fit. It matches a lot of the features that we see. For example, it matches the time of peak infection, that's the red dotted line, and it also roughly matches the peak height, so how many people are infected at peak infection time. And in addition, we get an uncertainty quantification. So we can see by plugging in the uncertainty from this density what the uncertainty on the predicted infection rates look like. And this is obviously very useful because it allows you to gauge sort of what the error is in your model. Okay, second example is taken from modeling urban structure. So there's this model that is used, I think, quite extensively in the literature of kind of flow of supply and demand through a network. So the idea is that you have a number of, you have a network and you have a number of zones in the network that are kind of origin zones, meaning origin of demand, for example, households, consumers, and you have a number of destination zones in the network, retail centers, these sorts of things. And the origin zones are coupled to the destination zones through a network, and the demand from the origin zones flows to the destination zones, which supply the demand. And what we're modeling is the kind of the size of the destination zones. So how does the supply adjust to the demand? And in this particular model, you have a set of equations that describe the size, Wj, of the destination zones. And the differential equation, it's sort of, if you look at the top equation, it's sort of a logistic equation, meaning that the rate of change of the destination zone depends both on the size and something that looks like 1 minus the size. So I'm talking about this, people online can't see, but the Wj and then the 1 or the dj minus k Wj. So essentially what this means is that initially you grow and grow and grow, and the rate of change is proportional to the size you already have. And then there's a sort of inflection point where there's a cost associated with having a certain size, and your size starts to decrease again. So there's a sort of optimum point.
So could size in this case be equivalent to congestion on a road or something like that?
Size would be something like retail floor space. I'll give an example.
Okay, so that's physical size.
It can be, well, I mean, you can apply the model to all sorts of abstract scenarios. So what the application I'm going to present is retail floor space. So yeah, maybe just think of retail floor space in a sense. Initially you can grow, but then eventually there's a cost associated with having a certain size. You have to pay rent, you have to pay utilities, etc., etc. So the kind of optimum, size. And the demand, so the total demand dj at a single node is essentially just summing over all the incoming demand from the origin sizes, weighted with the network weights. And the network weights kind of represent the cost of supplying demand through a certain route. So it's things like, it could be something like transport times, it could be something like transport distances, costs of transport, these sorts of things. I'll give an example again in a second. And and there are a couple of scalar parameters in the model. So there's kappa, which is the cost parameter, how expensive is it to maintain certain floor space, let's say. There's epsilon, which is a sort of responsiveness parameter, how quickly can the network respond to fluctuations. And then there are these, then there's alpha and beta. Alpha is the kind of size parameter, so it models how much emphasis do consumers place on size, the size of, let's say, a store. Do they prefer small stores to large stores? So that's the alpha parameter. And beta coupled to the network, so it's the kind of convenience parameter, how much emphasis do people place on having a conveniently located shop. Do they want stores that are nearby, or do they not care about travel? And in this example, what we want is we want to learn the parameters alpha, beta, kappa from observations of the steady state. So if you run this model for a sufficiently large number of steps, it will converge to a steady state. And what we do in this example is we observe the steady state, and we want to extract these three scalar parameters from the steady state. We can't learn the epsilon parameter because the dj minus kappa wj term will be 0 in the steady state, so you can't get the epsilon parameter. And the data set we looked at was retail floor space and household income. So the origin sizes are the ward level household incomes, cumulative, the total ward level household incomes. Those are the blue dots. And the red dots are major retail centers. So we looked at retail centers that are above a certain annual income or something. There was a classification done by the Greater London Authority. And the network, and then we looked at two different network metrics. We looked at travel times, so either driving or public transport. And we looked at travel distances. So not the Euclidean distance, but the actual road distance, which you can sort of extract from Google Maps. And then you get these two different metrics. And we do the same thing. You can't really see the yellow line, unfortunately, but we kind of run the model, we extract parameter marginals for the different parameters using both the metrics, so the spatial metric and then the yellow line here, should change that. The temporal metric, so the travel times and the travel distances, and you get a good estimate. And what we also did was to look at two different noise regimes. So I forgot to mention that in the introduction. But if you go back to this system, of course, the data that you observe can be noisy. And when you have a numerical solver, what you can do is you can run the numerical solver with noise, you can run it without noise, if you wanted to fit noiseless equations to a noisy data set. You can, of course, also learn the noise level itself. So this is what we did in the SIR example. And what we're doing in this example is, because we're just observing a single steady state, so we're just observing a single snapshot of the system, we can't learn the noise level because we don't have a time series, so we don't know what the noise level is. And there was a previous study done also by Mark, where they tried to estimate the same parameters using an MCMC. And what they did in that study was they just ran the model twice, once with an assumed low level of noise and once with an assumed high level of noise. And we just kind of took the same values and compared results. And so the MCMC estimates for the parameters are this beige line, probably, yeah, it's not very visible, but and then we can again compare the mean square prediction error, so how good is the calibration. And what you can see here is the mean square prediction error for our method tends to be 2 to 3 orders of magnitude better than with an MCMC. So we get 3 orders of magnitude improvement in the low noise regime and 2 in a high noise regime. And the other improvement you get is in computational performance. So the MCMC method takes 3 to 7 hours to run on a regular laptop, and the neural scheme takes about a minute on the same computer. So it's a massive performance improvement, and you get a significantly better calibration of physical equations. Okay, so those two examples were fairly low dimensional, so we're just learning like a handful of parameters, 2, 3 parameters, 4 maybe. We also looked at the other end, so what happens if you want to learn hundreds of thousands, millions of parameters for a system. And in this example, what we're doing is we're looking at the British power grid. And what we want to do is we want to learn, or we want to infer the location of the line failure from observations of the network response dynamics to the line failure. So you can model power grids using the Kuramoto model of synchronized oscillation. I don't know if you're familiar with it. It's essentially a model of coupled oscillators on a network. You have a bunch of oscillators. They can oscillate, obviously, coupled with a network. And what you observe over time is that their phases will synchronize. So you get this, for example, in bridges like resonance catastrophe. People walking over a bridge synchronously will cause a resonance catastrophe and can cause the bridge to fail. And you get it in things like heartbeats, actually. So, for example, babies in the womb and the mother's heartbeat will synchronize through this process. So you get a sort of synchronization process. And another example of power grids. So you have a large network of generators or power consuming nodes. They obviously oscillate at the grid reference frequency. And you see the phases will synchronize over time according to this model. And the model is has a couple of scalar parameters, modeling inertia, friction, coupling. There's some noise, and then you have this network AIJ here, which are the network of the electrical admittances. So the lines have an admittance, the higher the weight, the more strongly two nodes are coupled. And then each node either consumes or generates some power. It could be 0, it could be, for example, a power station. So the white circled nodes are actual power stations in the power grid. And of course, there are power consuming nodes, factories, and so on. And the model will equilibrate, and there's a condition for equilibrium, which is that the sum of all the PIs must be 0. What this means is that as much power is consumed as is put into the network. So the net power in the network is different. This is what, power grid companies do. They regulate the amount of power being put into the network to make sure that it stays at equilibrium. And so if everyone at 5 o'clock, everyone puts on the kettle for a cup of tea, power consumption goes up, so they have to put in more power to keep the network nice and steady. And what we did was we simulated the effect of a power line failure by cutting 2 edges in the northeast here and kind of recording the response. So this is the response here. We cut the line at t equals 0, and before you can see that the phases, so the y-axis of phases are in equilibrium. And then if you cut the line, if you cut these 2 lines, the network readjusts by redistributing the power loads along other edges. So because the power in the network is being held constant, it kind of has to redistribute the loads, and that triggers a sort of response cascade that ripples through the network until the network re-equilibrates. And what we want to do is we want to infer this location from observing these response dynamics. And what I'm showing here is the response to 4 different locations in the network, A to D. A and B are quite close to the power line failure, so it's sort of somewhere around York. The network is the real network, by the way, but the response, the power line failure is simulated. And you can see that the response is strongest at the nodes that are close to the power line failure, and they're much weaker elsewhere in the network, which is what you would expect. Like if a power line fails somewhere in Scotland, you're not going to really feel it, in Wales. But there is a response, fairly weak response, although most of the nodes will remain very close to equilibrium. So it's a highly underdetermined problem, actually, because you're not going to get any response at most of the locations in the network. We kind of do the same thing as before, so there is no fundamental difference in approaching networks and large parameter settings, and in the low parameter case, you just sort of take the network, you vectorize it, you have a really long vector of parameters, and that's what you want to learn to solve the equations. And so we train the neural network to find an adjacency matrix, a graph adjacency matrix that reproduces the response dynamics that we observe. And what I'm plotting here are the densities on the 3 edges with the highest prediction error. So these are essentially the top 3 candidate locations. And what you can see is that the top 2 locations are indeed the edges of the line failure. So I've marked them here. Oh, sorry, I've messed up the marking. Okay, you actually don't see what I want to see, but the numbers are wrong. These 2 edges are these 2 dotted lines here. And you can see that the predicted value, or the mode of the density, is at 0. And there's a small sort of secondary peak at the true value, that's the red dotted line. And for all the edges with a lower prediction error, you see that the prediction value is essentially the true value, so there is no change. And what's also interesting is if you plot, for example, the top 5 or 6 edges, they're all in the vicinity of the power line failure. So it detects the power line failure, but also sort of detects the general area. So and this is, not really surprising, because the response is strongest in this region. So you get the largest errors on the edges in the region around the power line failure. And again, the thing takes about half an hour to run on a regular laptop for a network of about 600-700 nodes, so about 500,000 parameters to be learned. And what it's doing is it's learning the entire graph adjacency matrix. So it's reconstructing the entire network. As I said, it's a very underdetermined system because most of the nodes have no response to this line failure. So what we did is we added an extra term to the loss function that kind of pushes the neural network towards the unperturbed network, because we know what the unperturbed network, so the network without the line failure, looks like, and we know that the network we're looking for has to be quite close to that, right? It couldn't be something wildly different. It can't be adding edges or something. It's going to be something that's quite similar to what the network without the line failure locations look like, and we added an extra term to the loss function. But even with that extra term, it's still a very underdetermined problem. So you couldn't, for example, use regression methods, which I'll come back to in a second, to extract the location of the line failure. And the other thing is that since it's so underdetermined, having densities is very useful because it allows you to do something like statistical hypothesis testing on the edges. So I'm giving you the p-values here as well, measuring the true value under the null of the line failure. In this case, the p-values are not really that necessary because it's such a clear-cut result. But that is partly because we simulated the response dynamics, so we get a cleaner, we sort of get a cleaner time series than we would have in reality. In reality, there'd be more noise involved, and there'd be sort of more oscillations in the scalar parameters. So you wouldn't get these sorts of very sharp peaks. You'd have more variance in the fit. And in that kind of situation, it's very useful to have p-values that give you some sort of way of quantifying the likelihood of measuring line failure. Okay, and the last example is same one I already talked about, the Harris-Wilson model. So it's again this model of the flow of supply and demand, except that this time we want to learn the whole network. So if we go back to the model, we now want to learn these network weights. And the difference between this model and the power grid is that this model is nonlinear in the network. So if you look at the equations, we're dividing by the network weights as well. This is a sort of normalization thing. If we go forward to the Kurimoto, this model is linear in the network, in the AIJs. So it's nonlinear in the network adjacency matrix, but we use the same data. We use the observations of sort of flow data in Greater London as the initial condition. Then we generate a synthetic time series, and we generate a time series that is just long enough to give us enough data to completely infer the network. So we kind of convexify the problem. And because we're interested in learning the entire network, the question is, well, how do you sort of quantify the uncertainty on the prediction? So in the case of the power grid, because we're just interested in essentially a small number of edges, it's fine to plot the density on the predicted on the edges. But if you're learning a network with 1 million parameters, it doesn't make sense. You can't plot 1 million densities, obviously. So you can, but what you can do is you can exploit the fact that networks have topology. So they have things like degree distributions, triangle distributions, shortest paths, etc. And you can quantify the uncertainty on the kind of high-level topological properties of the network. For example, the degree distribution. So here on the right-hand side, I'm showing the predicted network degree distribution. That's the solid blue line. So it's the degree distribution of the inferred network. And the solid red line is the true degree distribution. We're again using the Google Maps transport times network, I think. And you can see that it's a pretty good fit. This is using noisy data, so we added some noise to the time series. That's not a perfect fit. And in addition to the prediction, which is the maximum likelihood estimation, in this case, you get some uncertainty. That's this blue shaded area. And the uncertainty you get the same way you get uncertainty in the low dimensional case by tracking the neural network as it traverses the parameter space. You record the graphs that it tests and sort of create an uncertainty density by sticking them all together and getting uncertainty configuration. And again, this is a network that think about 100,000, 50,000 parameters, and it takes about 4 minutes to run on a regular app. Okay, the last two slides, I just want to give you some sort of performance metrics and talk a little bit more about the uncertainty quantification thing. And I'm going to stick with the network case, but it really applies to the low dimensional examples as well. But for the network inference problem, if the system is linear in the graph adjacency matrix, you can use a regression scheme if you just want to estimate the network. I can go into the details if you want, but essentially because it's a linear problem, you can invert everything and get an expression for the adjacency matrix as a function of the observation. It does involve matrix inversion, which is why you can only use OLS for the fully determined problem. So with the regression scheme, there is an inversion involved. And the inversion depends on having a sufficiently large number of linearly independent observations. Actually, you need at least as many observations as you have nodes. And typically you need more because there are sort of symmetries in the data. So what we did is we just generated enough synthetic data to be able to apply OLS to compare the prediction errors. And that's what I'm showing on the left. This is the prediction error, so the error between the predicted and the true adjacency matrix as a function of the noise on the data, the noise on the trained data. The yellow line is the OLS curve, and the black line is the neural scheme. I really need to stop using yellow for these.
Yes.
Yeah. And what you kind of see is that the OLS scheme for the virtually noiseless case, so everything below about 10 to the minus 4 really is virtually noiseless. So you wouldn't see the noise on the data. And for the noiseless case, the OLS, which is using linear regression, outperforms the neural scheme. You can see that there's a sort of residual error that remains as the noise goes to 0. But as soon as you start adding some kind of noise to the data, which is what you would have in almost all real-world applications, right? The predicted performance of OLS decreases quite strongly, and the neural scheme manages to maintain a somewhat robust performance up to low noise levels of about 10 to the minus 3, and then it goes up. The reason for this is that the neural scheme is inherently stochastic. It uses a gradient descent algorithm to find a minimum, but it doesn't hit the minimum precisely. It sort of bounces around the minimum. So there's always going to be some error involved. You can see that as the noise goes to 0, there's a residual error. This is because it's just sort of wandering around the minimum, whereas OLS will hit the minimum perfectly in the noiseless case. But in the noisy case, it doesn't do it well because it's not as robust to the introduction of noise. So you get better predicted performance on noisy data using this neural scheme. And the other thing is that using regression for graphs, as I said, requires inversion of an n by n matrix, and that typically is cubic in n. So the matrix inversion, actually there are more efficient algorithms that I think run in like n to the 2.5 or something, but it's between n to the 2.5 and n cubed. Whereas the neural scheme is quadratic in n, so actually linear in the number of parameters you're estimating. And if you're estimating an n by n matrix, you have n squared parameters you're estimating. So the networks, it's quadratic in the number of nodes. And what I'm showing here is the time it takes to do a complete network inference using ordinary squared and running one epoch of the neural scheme. So the neural time is just one epoch being the complete pass over the training set. You need to do several epochs to get good results, but it's linear in the number of epochs. So overall, the neural scheme is quadratic in n, linear in the number of epochs, and regression is typically cubic in n, which means that you just can't do, it's just infeasible for networks with say 1,000 nodes, which is even that large. Whereas in the neural scheme, you can run on a laptop for a network of 1,000 nodes. Okay, and the last thing I want to mention is I've talked a lot about uncertainty quantification. And uncertainty in these sorts of problems arises from two sources. It arises from the non-convexity of the loss function. So how many networks, how many parameters can fit the problem at hand. And that's the first source. And the second source is just noise on the training data. And what you want is for the uncertainty on your predictions to reflect both, right? You want to have a handle on how noisy is the data and how does that noise translate to my predictions. And you want to know, well, how many different parameters are actually compatible with the problem I have. And both things are important. So it's not really enough to just get a prediction. You want to know, are there other predictions that will fit? And what I'm showing here is that the uncertainty measure that we're proposing reflects both. So on the left, I'm quantifying the convexity of the loss function. We're again looking at the neural case, and in the linear case, you can quantify the convexity by looking at the rank of the matrix that you want to invert. point is just that as the convexity of the loss function increases, so as the solution becomes more and more unique, the uncertainty on, I'm showing here the predicted degree distribution, goes down. And again, you can see that there's a residual uncertainty as the problem becomes completely convex. So even in the fully determined case, there is some variance on the prediction. I'm never going to get a sharp delta peak. And this is because of the internal uncertainty on the weights and biases of the neural network. So this is due to the stochastic nature of the approach. And here I'm showing the uncertainty as a function of the training noise. So as you increase the training noise, the uncertainty on the predicted degree distribution goes up. And again, there's some residual error as the noise gets to zero. What I'm showing here, the black lines are the Hellinger metric. So that's some certain way of measuring the distance between distributions. But it's not an artifact of this particular choice of metrics. So you can also, for example, use the relative entropy to quantify the error on the degree distribution, and you get the same behavior, just different numerical values. So it's not an artifact of the choice of metric. It is sort of inherent in the scheme. Okay. So just to wrap up, you get from this method, what you get is a pretty high prediction accuracy. And the reason you get this high prediction accuracy is that you typically have a very high sample density around the minimum of the problem. Because the neural net uses a stochastic gradient descent algorithm to drive itself towards the minimum of the problem, you have a high density around the regions of interest. You don't have the problem that you have with other sampling schemes, that you sort of wander around these low probability regimes for a while before you sort of start to gravitate towards the minima. And this is why we saw that it outperforms MCMC in our experiments, and it outperforms OLS in the noisy case, at least, for the reasons I gave. Then you have a very high computational performance, and these are sort of, these reasons are sort of a bit hand-wavy, but this is really something we want to explore in future research. But I think what contributes to the computational performance is, first of all, you're not rejecting any samples. So you're using every point you sample along the neural net trajectory contributes to the probability density. Or at any rate, you have a reduced burn-in time, but other sampling schemes you have to throw away a lot of samples because otherwise you'd be overestimating the low density regimes. And with this, we didn't have to use any burn-in so far. So it seems unlikely that there would be no burn-in, but yes, the burn-in seems to be reduced at any rate. And then, of course, you're not solving the inverse problem. You can use very efficient ODE solvers that are there. You can increase the sample density by running the neural scheme multiple times in parallel, which is what we have always been doing. And of course, you have all these super efficient pre-compiled machine learning libraries that you can use for auto differentiation, so you don't have to write the gradient descent algorithm yourself, for example. It's pretty robust under noise. One thing I didn't show with the Harris-Wilson model. So these are the estimates for the high noise regime. And if you look at the estimates for the low noise regime, they're quite similar, just with a reduced variance for the neural scheme. But for the MCMC, you get completely different estimates. So the MCMC depends very delicately on sort of the assumed underlying noise level, which you wouldn't expect, right? You would expect the prediction to be independent of your choice of noise that you're assuming in the model. You would expect to get a higher variance, but you wouldn't expect the prediction to be vastly different. And so our scheme in general seems to be able to deal with noise quite robustly. You get meaningful uncertainty quantification, as I said. It's mathematically and algorithmically very simple to implement, fairly simple to implement. There's not a lot of sort of tempering and all these sorts of things going on that you have with other sampling schemes. And it's flexible in that it seems to be very applicable to lots of different types of problems. So you can use it on time series data, steady state data. You can use it for different parameter types, networks, individual parameters, noisy, noiseless data, convex, non-convex problems. It doesn't depend on you having enough data to fully determine the problem. And it works for linear, nonlinear equations, different types of equations. But of course, and this is, I think, the thing that sort of plagues a lot of these neural schemes, is that you don't have a particularly good handle on the sort of theoretical convergence properties. So in particular, what we don't yet know is how does the convergence rate depend on, let's say, the neural net architecture. And so there's a lot of sort of fine-tuning the neural network involved by doing, hyperparameter optimization, these sorts of things to sort of find the ideal configuration for a particular problem. And one big question mark is, and I haven't really addressed this, but this whole scheme requires a certain degree of differentiability in the underlying physical equations because it's a gradient descent algorithm, so it works using derivatives, obviously. So how does this form if, for example, you have a step function, or if you have a non-differentiable function in your equations that you can't approximate with a smooth function? If the functions have subgradients, it's fine, so you can use absolute values, that sort of thing. But in the really non-differentiable case where you only have like weak derivatives, we haven't yet explored this, so this is something that we'll be looking at. Yeah, so thanks for listening. There's a code repo with all the examples and code available, and it's sort of written to be adaptable to new ideas, and it's thoroughly documented. And yeah, these are the articles. Thanks.